Welcome to our quantum deep dive.
Glad to be diving in.
Today, we are really going deep into the tiniest scales imaginable to talk about something absolutely fundamental, the up quark.
That's right, essential stuff.
And our guide for this exploration is a really insightful essay, Up Quarks, Fundamental Baustein der Quantentechnologie by Jörg O. Schneepatt.
A great piece to work from.
So our mission today, basically, is to pull out the key insights, the really crucial bits about up quarks from Schneepatt's work.
Sounds good. And up quarks, as Schneepatt really clearly lays out, they're part of this quark family. Elementary particles, the bedrock of the Standard Model.
Right, the fundamental ingredients list for the universe.
Exactly. Think of them like essential Lego bricks. They build protons and neutrons, the things inside the nucleus of every atom.
And what holds these bricks together?
That's the strong force. It's described by this theory, sounds a bit intense, quantum chromodynamics. QCD for short.
QCD, okay. So up quarks, fundamental in protons, neutrons, strong force holding them. Got it. What else, according to Schneepatt, are the absolute must-knows right away?
Okay, well, first up, they're fermions. That means they have this quantum property called spin, specifically spin 1/2. It sounds abstract, but it dictates a lot about how they behave.
Spin 1/2. Check.
And they're in the first generation of quarks. That just means they're among the lightest ones, most common ones.
Makes sense. Lighter usually means more fundamental somehow.
Kind of, yeah.
Yeah.
And, crucially, their electric charge. It's not a whole number like an electron's -1. It's plus 23 of the basic unit of charge.
A fractional charge. Okay, that's definitely weird.
It really is one of the most unique things about quark.
Fractional charge, key part of matter. This is where it gets really interesting, right? Schneepatt's essay digs into their fundamental properties. What are the key things there?
Well, what's fascinating is how light they are. They're one of the lightest quarks, yet they feel all three of the main forces: strong, weak, and electromagnetic.
All three. Wow.
Yeah. Now, figuring out their exact mass, that's tricky. Really tricky experimentally because of something called confinement in QCD, which we'll definitely get back to.
Okay, confinement. We'll park that for a moment.
Right. Schneepatt gives a value, around 2.2 MegaT. But here's the mind blower. That tiny mass, it's almost nothing compared to the mass of a proton or neutron.
Wait, what? How does that work?
Most of the mass comes from the energy of the strong force, the binding energy holding the quarks together. It's like the energy you put into mixing cake ingredients being way heavier than the flour and sugar themselves.
So these tiny things are mostly made of glue, the energy holding them. That's wild.
It really is. And the essay also brings up this idea of color charge. What's that about?
Color charge. Okay, don't think of paint. It's the strong force equivalent of electric charge. But instead of just plus and minus, you've got three types: red, green, and blue.
Red, green, blue. Okay.
And the particles carrying the strong force, the gluons, they also carry color. So there's this constant, furious exchange of gluons and colors between the quarks. That's what binds them so tightly.
A constant dance inside the proton.
Exactly. And here's the kicker. Only combinations that are color neutral or white overall can exist freely, like mixing red, green, and blue light gives you white light. Same idea.
Which explains why we never find a lone quark wandering around. Precisely. They're always locked in these color-neutral teams. It's all captured, mathematically anyway, in the QCD Lagrangian. That's the equation for the strong force.
The unseeable building block. Okay, Schneepatt also compares up quarks to their cousins. How do they stack up against, say, down quarks?
Good comparison. Down quarks are very similar, just a little heavier, and their charge is different. Manic 13. But same spin, also first generation. They're the up quark's partner in making protons and neutrons.
So up and down are the main duo for everyday matter. What about others, like the strange quark?
Strange is, well, stranger. It's quite a bit heavier than up or down, also has an heavily 13 charge, but it's involved more readily in weak interactions. You find it in particles that aren't stable parts of atoms, like kaons, more exotic stuff.
Exotic hadrons, right. Now, stability. Up quarks are inside protons, and protons last basically forever, right? Does that mean up quarks themselves are immortal?
Well, inside a proton, which is two ups and one down quark, remember, an up quark doesn't really have anywhere cheaper energetically to go via the strong force. So yeah, in that context, it's incredibly stable.
But not absolutely stable.
Oh, not technically. The weak force can change things. Think about beta decay. A neutron, one up, two downs, turns into a proton, two ups, one down. What's happening there is a down quark is flipping into an up quark, spitting out an electron and an antineutrino.
So quark flavors can change via the weak force.
Exactly. And the reverse, an up changing to a down, can happen too, though it's much rarer in normal conditions. But despite this weak interaction possibility, the proton itself, with its two up quarks, is phenomenally stable. The up quark is just part of a very, very stable setup.
Okay, that makes sense. It's stable within its family. Now, moving on, Schneppat's essay really stresses their role in this standard model. It's not just about being there, right?
Not at all. They're fundamental actors. As Schneppat points out, their existence defines protons and neutrons. And their specific charges, the plus 23 for up and negative 13 for down, add up perfectly to give the proton its plus 1 charge and the neutron its 0 charge.
The math checks out.
But it's more than just accounting. That constant gluon exchange we talked about, that is the strong force binding the nucleus together. And again, the energy wrapped up in that interaction, that's where most of the mass of protons and neutrons comes from. Confinement and mass generation, all tied together.
So they're not just in the forces, they're actively mediating them or involved in them, and not just the strong force, you said.
Correct. All three fundamental interactions relevant at these scales. Strong force via gluons, obviously, captured by the QCD Lagrangian. Electromagnetic force via photons, because they have electric charge, governed by the QED Lagrangian.
QED, quantum electrodynamics.
Right. And the weak force, through W and Z bosons. That's the one that allows those flavor changes, like down to up in beta decay. It seems subtle compared to the strong force's grip, but it's absolutely vital for things like, well, nuclear fusion in stars.
Fusion. Schneppat also mentions electroweak unification. How do up quarks fit into that picture?
Yeah, that's a deeper level of understanding. Electroweak theory shows that at incredibly high energies, think the very early universe, the electromagnetic and weak forces weren't separate. They were unified.
One single force.
One single electroweak force. As the universe cooled, the symmetry broke, and they split into the distinct forces we see now. The strong force, QCD, stayed separate, and it becomes the dominant player at the lower energies inside protons and neutrons, keeping those up quarks locked up.
So, high energy, unified, low energy, distinct forces, with strong force ruling the roost inside nucleons.
You got it. It's about the energy scale.
And connecting this back to the bigger picture, the cosmos, how do these tiny up quarks shape the universe according to the essay?
Well, zoom out, and their role in protons and neutrons directly sets the structure of atomic nuclei. The whole periodic table, the stability of elements, it all hinges on the balance of protons and neutrons, which means it hinges on the up and down quark content.
So, chemistry starts with quarks, essentially.
In a very real way, yes. And think about stars again. Stellar fusion, the process powering stars, fundamentally involves protons rich in up quarks fusing together. That process relies on the weak interaction changing protons to neutrons sometimes, which means up quarks changing flavor. So up quarks are indirectly powering stars and creating all the heavier elements.
Wow, from the incredibly small to the astronomically large. Okay, the essay then shifts into the quantum mechanical side. How are up quarks described there?
Right, this is where things get properly quantum. Schneppat explains they're described by wave functions. These aren't little balls anymore, but probabilities, telling you the chance of finding a quark in a certain state.
Probabilities, not positions.
Exactly. And even more fundamentally in quantum field theory, or QFT, an up quark isn't even a particle in the classical sense. It's an excitation, a ripple, in the up quark field denoted UX. And this field obeys the Dirac equation.
The Dirac equation that connects quantum mechanics and relativity. Right?
Precisely. It's the equation for spin 12 particles, like quarks and electrons, moving near the speed of light. It naturally incorporates their spin.
And that spin, you mentioned it earlier, how does that show up in this wave function or field picture?
The wave function or the field excitation has two possible spin states. We often call them spin up and spin down. It's an intrinsic angular momentum, a purely quantum thing, and it affects how they interact with magnetic fields and other particles.
Okay. Now, the essay also talks about quantum fluctuations in the vacuum. This sounds weird, like something from nothing.
It does sound weird, but it's a real consequence of quantum mechanics, specifically the Heisenberg uncertainty principle. You know, the one that says you can't know energy and time perfectly simultaneously.
Oh, true. That one.
That one.
Yeah.
That little bit of uncertainty allows energy conservation to be borrowed for incredibly short times. Long enough for particle-antiparticle pairs like an up quark and an anti-up quark to just pop into existence from the vacuum and then annihilate almost instantly.
Virtual particles, so they're not really real.
They're real enough to have effects. Inside a proton, for example, these fluctuations contribute to what's called the C, of virtual quarks and gluons. It's not just the three valence quarks in a proton. There's this whole churning sea of virtual pairs influencing things. It affects the effective mass of the quarks and the overall structure.
So the inside of a proton is a really busy place.
Incredibly busy. Physicists use complex computer simulations, lattice QCD, to try and model this chaotic internal world.
Lattice QCD. Right. And Schneeppot brings up the QCD Lagrangian again here, linking it to confinement and something called asymptotic freedom.
Yes, these are two crucial and kind of opposite features of the strong force, both described by that one QCD equation. Confinement is the idea that the force between quarks gets stronger the further apart they get, like a bizarre rubber band that pulls harder the more you stretch it.
Which is why they're always stuck together.
Exactly. Try to pull one out, and the energy required becomes infinite, creating new quark-antiquark pairs instead. But asymptotic freedom is the flip side. At very high energies, or equivalently very short distances, the strong force becomes weak.
Weaker when they're close. That's counterintuitive.
Totally. It means inside the proton, when quarks are very close, they act almost like free particles. It's only when they start to stray that the strong force really yanks them back.
Okay, confinement holds them in. Asymptotic freedom lets them rattle around a bit inside.
That's a good way to put it.
And Schneeppot gives concrete examples of particles with up quarks.
Yeah, just to ground it. Baryons 3-quark particles like the proton and neutron are the obvious ones, but also mesons quark-antiquark pairs like the pion, which can be an up and an anti-down, or the kaon, an up and an anti-strain.
Pions, kaonons. Important in nuclear interactions too, right?
Absolutely. They mediate forces between protons and neutrons in the nucleus, and they show up in particle decays and astrophysical processes. Up quarks are everywhere in the particle zoo.
Okay, now for a really interesting turn the essay takes. Potential technological applications. This sounds very future forward.
It is definitely speculative, very much theoretical at this stage. We can't just, grab an up quark and build something with it yet.
Right. Confinement kind of gets in the way.
It does. But Schneeppot outlines some fascinating ideas, especially around quantum tech. One thought is using that color charge we talked about. Could that property be harnessed for quantum information?
Using color as a quantum state.
Potentially. And maybe the fact that quarks must bind into color-neutral states could offer novel ways to build in error correction for quantum computers, which is a massive hurdle right now.
Error correction is key. Could the strong force itself be useful there?
Again, speculative, but maybe. The sheer strength and the nature of that binding could lead to more robust quantum states. Schneeppot also talks about using quantum computers to simulate QCD.
Using quantum to understand quantum.
Exactly. Running lattice QCD calculations on a powerful quantum computer could give us insights into quark behavior that are impossible with classical machines. Understanding that Hamiltonian system, the energy dynamics, in detail.
The essay even floats this term qubits. Quark-based quantum bits.
Yeah, sounds cool, doesn't it? It's the theoretical idea of using quarks themselves as the basis for qubits. Maybe using the entanglement between quarks inside a hadron, or using the 3 color states to make it quite a quantum bit with 3 levels instead of 2.
Beyond binary quantum computing.
Perhaps. And maybe the strength of the strong force could even make these qubits inherently more stable than other types. It's blue sky thinking, but grounded in the fundamental properties.
So the very fabric of protons could become computational components.
That's the dream, however distant. And quantum computers simulating QCD accurately could feed back into our understanding, maybe even impacting material science down the line, if we understand how matter is built at that level.
And Schneeppot mentions other possibilities too, beyond computing.
Briefly, yes. Very theoretical ideas about quantum communication. Could the unique binding rules of QCD inspire new kinds of quantum key distribution for ultra-secure communication? Maybe even analogies to topological quantum computing concepts.
Wow, okay, definitely food for thought there. It really drives home how fundamental this stuff is.
It really does. The potential connections are vast, even if the path isn't clear yet.
So finally, let's talk about the proof, the experimental evidence. How do we actually know all this if we can't see a lone up quark?
That's the million-dollar question, experimentally speaking. It's all indirect. High-energy collisions are key. Schneeppot rightly points to the deep inelastic scattering experiments back at SLAC in the late 60s. That was huge.
What did they do?
Basically, they fired high-energy electrons, like tiny probes, at protons. And the way the electrons scattered off, it wasn't like hitting a single solid ball. It was like hitting something with Smaller, hard bits inside.
The first glimpse of quarks.
The first strong evidence, yes. Analyzing that scattering pattern, using equations involving things called structure functions like F, X, Q, at G, allowed physicists to map out the momentum distribution of charged point-like particles inside the proton. Quarks.
Like throwing tennis balls at a piñata and figuring out the candy inside from how they bounce off?
That's a fantastic analogy. And today, we use much higher energy tennis balls at places like the LHC at CERN.
The Large Hadron Collider.
Right. When protons collide there at incredible energies, the quarks and gluons inside interact violently. They produce sprays of particles called hadron jets.
Jets of new particles spraying out.
Exactly. By carefully measuring everything that comes out in detectors, huge, sophisticated instruments like ITLAS and CMS, we can reconstruct what happened in the collision and learn about the quarks involved. We also study the properties of the baryons and mesons produced, and deep inelastic scattering is still used, getting ever more precise.
And CERN is the main place for this now.
It's definitely a major hub. The LHC experiments like ITLAS and CMS looking at quark dynamics, and ALICE specifically studying the quark-gluon plasma. It's central.
Quark-gluon plasma, that state where they are free.
Sort of free, yeah. That incredibly hot, dense state thought to exist just after the Big Bang. ALICE creates tiny droplets of it. But Schneepat also mentions other crucial labs, Fermilab in the U.S., which has made huge contributions. SL at Sea, where it all started. Keiki in Japan. It's a global effort.
A worldwide quest. But even with all this, Schneepat points out there are still big open questions about up quarks.
Oh, absolutely. Big ones. Like we have QCD, this incredibly successful theory, but we still lack a rigorous mathematical proof for confinement. Why are they always trapped? We can calculate it, simulate it, but we can't quite prove it from first principles easily. That's the quark confinement problem.
We know it happens, but not quite the deep why.
Pretty much. Then there's the quark-gluon plasma, understanding its properties fully, its role in the early universe. That's ongoing work for Alice and others.
What else?
Well, is the quark truly fundamental? Or is there something even smaller inside? That's the idea behind prion theories, though zero evidence so far.
Layers within layers.
Maybe. And then there's the whole matter-antimatter asymmetry puzzle. Why is there so much matter and so little antimatter? Subtle differences in how quarks and antiquarks behave, known as CP violation, are part of the picture, and up quarks might play a role we don't fully grasp yet.
And looking beyond the known physics.
Right, the search for physics beyond the standard model. Theories like supersymmetry predict partner particles for quarks, squarks. Other theories involve extra dimensions or new forces. If any of that is real, it would likely connect to quarks, including up quarks, in new ways.
So the up quark story is far from over.
Not by a long shot. Lots of mysteries left to solve.
Well, as we start to wrap up this quantum depth dive, it's just incredibly clear. Up quarks, as Yurgo Schneepat's essay really highlights, they're not just tiny particles, they are absolutely foundational.
Couldn't agree more. They define matter as we know it.
They're central to the fundamental forces, especially the strong force via QCD. They shape atomic nuclei, fuel stars, and yet there's still so much we're trying to figure out.
Exactly. We've touched on their basic properties, their place in protons and neutrons, their role in the standard model, the ongoing experiments, but the open questions remain.
And the potential, however theoretical right now, for future tech based on understanding them better, like in quantum computing, it's mind-bending.
It really pushes the boundaries of what we think is possible.
It really leaves you wondering, doesn't it? If something as seemingly simple as an up quark underpins all this complexity and holds these deep secrets, what other basic parts of our universe might be hiding equally profound truths?
That's the beauty of fundamental physics, I suppose. The deeper you dig, the more questions and the more potential wonders you find. And we should definitely thank Yurgo Schneepat again for the essay Up Quarks, Fundamental Baustein der Quantentechnologie, which really spurred this whole discussion.
Absolutely. A fantastic foundation for today's deep dive.
Well,